Another way that we look at these, okay, now we're ready, now that we understand the concept of a polar bond, I think, now we want to look at the concept of a polar molecule. And in order to have a polar molecule, the molecule itself must have polar bonds. Okay, the electron clouds need to be unequally distributed across the bonds. So in the case of water, of course, there's two OH bonds, and the hydrogen is going to be the partially positive bond, part of the bond, and the oxygen is going to be the partial negative because oxygen is more electronegative than hydrogen. And this is another way to show the electron cloud distribution. The blue is indicating regions of partial positive charge, and the red is region of partial negative charge. And so you can see that in this molecule, you know, it's not really just an H, no, and an H, but it's you know, it's protons and neutrons and electrons, and the electrons are not equally distributed. There's more electrons on this side of the cloud than on this side of the cloud. And so in this case, we're showing that the electron cloud is not evenly dispersed. Okay, so from this picture, you should be able to maybe define a polar molecule yourself and try to figure out what is it about this molecule and would it be considered polar. Okay, let's think about that for a minute. All right, so far we've just talked about the bond. Now we want to figure out how do we know if a molecule is polar or not. Okay, and I think you've figured out what's going on here, but let's just march through this systematically. Here's an example. Are these molecules polar or nonpolar? We've got carbon dioxide and water. They're both molecules, covalent compounds. They both have 3 atoms in them. In this case, there's 1 carbon and 2 oxygen. In this case, 1 oxygen and 2 hydrogens. So as far as the molecular formula goes, it's kind of very similar. 1 central atom and 2 terminal atoms between the two. Are the bonds within the molecules polar? Because in order to have a polar molecule, you have to have the bonds to be polar within the molecule. And the electronegativity value for carbon is 2.5 and oxygen is 3.5. So the electronegativity difference here is going to be, the difference in electronegativity here is going to be 1. So that's more than 0.3. So yes, this is a polar bond and this is a polar bond. Check. And this one we've already looked at. We know these OH bonds are polar. The electronegativity difference was 1.4. Check. Okay, so we've got the polar bonds. So how do we decide whether or not these two molecules are polar or nonpolar? Well, polar bonds means unequal electron cloud distribution across the bond. Polar molecule is unequal electron cloud distribution across the entire molecule. All right, and so what you see in the case of water is that the negative charge density is greater on this side of the molecule than that side of the molecule. So in the case of the carbon dioxide, you've got greater electronegativity, but it's the same on both ends. And if you look at this side of the molecule compared to that side of the molecule, it looks like the mirror image. And if you were to slice it across the other axes, it would look exactly the same on top and bottom. Left and right looks the same, top and bottom looks the same. So in this case, what happens is the charge distribution, although uneven in the bond, it gets balanced out over the whole molecule because the molecule is symmetric. Okay, so even though there are polar bonds within the molecule, the electron cloud distribution cancels each other out. And so in the case of a symmetric molecule with polar bonds, the molecule itself is actually nonpolar. In the case of water, if you slice it down this way, the left-hand side looks like the right-hand side. But if you slice an axis across this way, the top looks different from the bottom. So in this case, this is an asymmetric molecule. It's not symmetric. And therefore, the unequal electron distribution is not balanced. And so this molecule would have a positive end down here and a negative end up here. And so in this case, this particular molecule would be considered to be polar. Okay, so going back to the picture here, looking at different types of compounds, the charge is not equally distributed there. And so that molecule, the water molecule, is polar. Okay, let's see here. All right. So the next, consider this activity just goes back through what we just talked about. So you want to try that on your own and see if you can, without looking back at what I just did, go through these questions and answer them using some reasoning like we just did. And then look back at this molecule here. You've got methane and water. And in this case, again, we've already decided that water is polar because the charge is not equally distributed. Carbon and hydrogen do have different electronegativity values such that they are polar bonds. But the case of the tetrahedral arrangement here that we see, it has symmetry. If we slice it down this axis, these two sides looks the same. If we slice it across this axis, these two sides looks the same. It doesn't matter how you slice it, this molecule is symmetric. Whenever you have a tetrahedral arrangement such as this, even though it may not look symmetric, you should probably build a model and look at it from all the different sides and prove to yourself that no matter how you flip it or turn it, it looks exactly the same. So as long as all the atoms in the bonds are the same, then a tetrahedral arrangement will be symmetric. Okay, if you change out the atoms, then you're going to change up the symmetry of the molecule, and you may lose that symmetry. So this one is symmetric, this is asymmetric. So this is polar, of course, and this is nonpolar. All right, so we have a way of looking at molecules and deciding whether or not they're polar or nonpolar, and just some basic rules. First, of course, you have to determine the Lewis structure and the molecular geometry. You've got to know what the thing looks like before you can decide whether or not it's polar or nonpolar. Then you have to identify, are there polar bonds within the molecule? Once you do that, then you look for the symmetry. And you're looking for different atoms or non-bonding pairs of electrons, which will mess up your symmetry on the central atom, that sort of a thing. So if the molecule contains polar bonds and is asymmetric, the molecule is then polar. So what I want you to do then is work in small groups. You can go back through and you've worked out all of these Lewis structures at one time or another, and remind yourself of the Lewis structures and the geometries of all these molecules, and then decide whether or not they're polar or non-polar.